Thank you very much for the kind invitation to talk here, and also especially to responding to my request for a little earlier slot, because I have to drive to Houston in a little while. So I much appreciate it. Also to Francesco, who agreed to the swap. All right, so I'm going to talk about more the theoretical aspects really of our T-matrix approach, not only to heavy flavor, but also try to make connections to the properties of the QGP itself. And let's go. Somehow it doesn't advance. Okay, I guess I have to get out.
Maybe you can, yeah, you can. Okay, now. And
something seems to be stuck. Okay, now it works. Sorry for that. And let me get my pointer back here. Yeah. Okay, there you go. All right, so I'll start out with some remarks on the general, maybe objective we have in mind to really relate the properties of QCD matter to the underlying forces using heavy flavor probes. So we have these beautiful lattice results here for the equation of state, and I think we all know that this matter here, especially in the near TC region, is a very complicated one. But we also have information on the more microscopic properties in the heavy quark sector in terms of these very nice free energy data. Now, it's not exactly a force, although it will be related to one. And as it turns out, actually, in the zero temperature limit, it is the heavy quark potential, which is, of course, very well established. Now, what the free energy data already tell us, and that is certainly not a surprise, that even above the critical temperature, there seems to be really still rather substantial non-perturbative effects. And sort of the goal then is to understand the bulk and maybe transport properties of the QGP in terms of these non-perturbative effects. So I think here heavy quark diffusion really can do us a great service, probing in particular the long-range forces in the medium that then are responsible for the non-perturbative structure and properties of the QGP. Let me follow that up a little more along those lines. Now, I think by now we would all agree that the QGP, at least for not too large temperatures, is a really strongly coupled quantum liquid with transport coefficients, which are actually not far from the conjectured lower bounds. Now, if that is true, and if you want to really understand the microscopic interactions that are going on there, our calculations of the transport coefficients should, in principle or ideally, be sensitive or even obey those quantum lower bounds. At the same time, since we're embedding the heavy quarks into the QGP when we're doing that transport, ideally we would also have a description, a microscopic description of the bulk medium through which the heavy quarks propagate that encodes those strong coupling properties, in particular in terms of the whatever the degrees of freedom are of the hot and dense QCD matter. If you can do that, or at least attempt that, then we also get the benefit that the various transport coefficients can be calculated from the same underlying interaction. And in this way, we can learn about, make connections between, say, what we find from hydrodynamic analysis or from our heavy flavor diffusion, of course, and even electromagnetic probes in terms of the electromagnetic electric conductivity. So what is quantum effects? They can come in various flavors, literally. But I think what is clear is that we really have very large scattering rates in the system. And that means large collisional widths of our excitations or degrees of freedom. And that, of course, means broad spectral functions. And it's really a question how broad they are. And it's then these broad spectral functions which encode the off-shell or quantum effects. So that, I think, is the main connection here for us. And in the following, I will try to highlight, as I go to our particular approach, highlight where they come in and to make maybe us all a little aware of what we mean when we say quantum liquid. All right, so here's my outline. It's rather compact, so I'll introduce the T-matrix approach and how we determine its key input, the potential, and then I'll discuss applications of it in terms of the bulk medium and the heavy flavor transport. So let's start with the T-matrix approach. Now this is a rigorous many-body approach that has been worked out many years ago in the context, in fact, of electromagnetic plasmas. And it is given diagrammatically here by this, scattering equation in full 4D. That would be the beta equation. And its key feature is that you resum the potential. Now you can recover the perturbative limit in terms of just the leading order of the potential. But if that potential is large, then a perturbative expansion will not work. And in fact, we have seen that explicitly that this is so for example, for heavy flavor, for the heavy flavor transport coefficient, the next leading order factor of 5 or more larger. That simply means the perturbative expansion doesn't work. So we really have to resum it. That is what is achieved then here. And what comes in then also is these intermediate particle propagators of the particles that interact. And these, of course, themselves are medium modified. They move through that, say, Quark-Gluon plasma. And the self energies that are induced, they also are usually resummed in what is called a Dyson equation. In this sense, these coupled equations are really, you could also call it the Dyson-Schwinger approach. And as is well known, the self energies in turn depend on the T matrix of the propagating particle I interacting with the medium particles J. And in this way, you have a self-consistency problem that usually you can solve by numerical iteration. So that framework is from a many-body point of view rigorous. So in a way, how good it is, it depends how well you can determine its input, which is mostly the potential in the first place. Now in the vacuum, we can resort to the Cornell potential in the heavy flavor sector. We know that is a very good spectroscopy for both Quarkonia and also, in fact, for open heavy flavor mesons. What it doesn't maybe do so well is the chiral aspects, the chiral sector of QCT, where other forces can come in, like NJL type or instanton forces. But in principle, they can also be implemented. So then we go in the medium and we have to address the question, what is really the medium potential? Now, I already said it's not the free energy and it's not the internal energy. So what is it? Well, we can actually calculate the free energy in terms of a quarkonium spectral function. And that quarkonium spectral function then has this driving kernel in the scattering equation as its potential. That is, in a way, the definition of the potential in the T-matrix approach. And as you see here, it's resummed, and it has the potential can have real parts and imaginary parts. And of course, you also have the single particle self energies that enter here. Now, first remark is we can still, starting from our vacuum baseline, write down in medium screen potential, and then really these screening masses, the Debye mass and the screening of the string term, they become parameters that you then have to determine at final temperature. Now that's easier said than done, because really once you have a potential, you have to calculate the self energies and you have to solve the self-consistency problem. And that actually turns out to be very important, as I will argue on the next slide. Before I go there, let me just say that if the imaginary parts are in fact very small, and then the spectral function here becomes a delta function, then you can immediately see by carrying out the delta function that the free energy is actually equal to the potential. But that is only if you have small widths. So the width or the quantum effect here is absolutely critical in determining the potential and make it actually stronger than what the free energy would provide. So what we then did is carry out this program and trying to find self-consistent solutions. It turns out you can actually find two solutions that we label the weakly coupled scenario and the strongly coupled scenario. And the resulting potential is shown here in these two plots. To the left, 494 MeV, and to the right for 400 MeV temperature. And what you see indeed, if you have, you can find a solution. For both solutions, first of all, the free energy can be accurately reproduced. But for the weakly coupled solution, the potential is just a little larger than the free energy. And sure enough, the imaginary parts are small. So we are not far actually from that delta function solution. On the other hand, there exists another solution, which is quite a bit more non-trivial and also not so easy to find. That is what we call the strongly coupled solution, where the potential is much stronger. And at the same time, well, if the potential is stronger, also the imaginary parts, and of course also the real parts, but they play a lesser role, are much stronger, much larger, factor 6 larger here in this case for the heavy quarks. So there exists this non-trivial solution that, however, is in a way self-limited, because it's a self-consistency problem between the strength of the potential and the magnitude of the width. As I argued before, it's the magnitude of the width which drives the potential away, but then it has to be consistent with the width or quantum effect. So the quantum effects and self-consistency, in a way, limit the coupling strength. You cannot go to arbitrary coupling. It is limited by the self-consistency in terms of the large widths. So that's what I would argue is the first manifestation of a quantum effect in this approach and determine, in fact, the potential. You can go further and do checks with other types of lattice data. Once you have the Quark-gonium spectral functions, you can straightforwardly calculate the Euclidean correlators and then compare them to lattice data. In fact, these were included in the self-consistent fit procedure just to have a better accuracy here. And you see in the germanium and the bottomonium sector, you get correlator ratios which are in reasonable agreement with lattice data. And what you find is that, yes, the J-psi dissolves, but not all that quickly. Maybe it's gone by 300 MeV or so, while the 1s survives much higher. And while I will not touch much on phenomenology in this talk, you can then use these kind of inputs, the binding energies and the widths, in your transport approach in particular. All right, so that brings me already to my second part, where I now want to make the connection to the open heavy flavor and in fact also the bulk medium. In fact, the bulk medium already played a role in what I discussed in the previous slides, because we had to evaluate in particular the spectral function, the self energies or spectral functions of the individual heavy quarks, which arise due to the interactions with the medium. So in fact, the medium is also part of that self-consistency, if you wish. And here it's, of course, very important to use also, again, a formalism for the equation of state that accounts for the quantum effects and is also conserving, yields a conserving approximation for the T-matrix approach. And that is precisely this Luttinger-Ward-Boehm formalism for which you can write the free energy of the QGP in terms of these in-medium propagators G and what is called this Luttinger-Ward functional, which includes all the interaction contributions. This is actually very challenging to compute, but my former graduate student, Shuai Liu, actually managed to numerically resum the ladder series in the presence of large widths, which is more complicated than the T-matrix because there are extra statistical factors in there which make it more complicated. So what you, the kind of, I should say, there are two more fit parameters then that come up, and these are what we call the bare quark and gluon masses that are related to Casimir factors that, however, we then adjust to reproduce the equation of state. So it's not maybe too surprising that we reproduce the equation of state, but what is important is if you look really under the hood of that, and what turns out is that this Luttinger-Ward functional phi, the interaction contribution, becomes larger and larger as you go smaller in temperature. And you better understand what that means if you actually look at the underlying 1 and 2 body spectral function. So here the solid lines are the quark spectral function and dashed lines are the T matrices, imaginary parts, in fact, in one specific channel, the color singlet channel. And what you see is that at the low temperature at 190, the quark spectral function is actually very broad. The broad is 600-700 MeV, and that peak here is actually collective excitation that you pick up. While you have a very large resonance strength, and it's actually not surprising, although we are very pleased to see that is essentially comes out at the raw meson mass. So we do recover also in that sense here the vacuum limit. As I said, we don't have chiral physics that would be needed for the pion. So the interpretation then really is, or what is going on here, is that at the high temperatures we have very small scattering rates, small interaction contribution, and the show is really run by quark and gluon quasi-particles, the blue one here. While at low temperatures, the resonance is built up in basically all attractive channels, the diquark and the color singlet quark antiquark, and that becomes the dominant contribution to the equation of state. So this again is a manifestation of quantum effects that the very large widths sort of screen out the quarks from the degrees of freedom because of the large widths, and the degrees of freedom are taken over by the composite states. So this then provides a consistent and with the heavy flavor part medium that we can use to evaluate our transport coefficients in. So let's have a look then at the quark transport coefficient. First, I show here the T matrix, which the two-body T matrix for heavy light scattering, and not surprisingly, much like in the light sector, the D meson comes up again pretty much at the right mass, 1.8 or 9 GeV. And it dies, however, really quick as we go up in temperature. So what does it? So these broad states emerge near TC, near the vacuum mass, and if you then look at the and this is, I should say, for the strongly coupled scenario. If you then look at the friction coefficient, the solid lines are the results for the strongly coupled, and the dashed lines are the result for the weakly coupled. What you see close to TC, there's really a very large difference factor, I don't know, 4 or 5 between the two solutions. At higher energies, they approach each other, but it's at higher temperatures, I should say. But it's really at the low temperatures where these strong interaction effects are most prominent, and they lead to actually this kind of almost constant behavior of the low momentum transport coefficient with temperature. And really what has happened there is that the increasing density of the partonic medium is compensated by the loss of interaction strength as you go up in temperature. So this is really a non-perturbative fact that there's not a whole lot of temperature variation there. On the other hand, if you go to the high momentum limit, you're supposed to recover PQCT, and by and large, you do. In particular, you get the correct temperature ordering again, and really the ratios of the coefficients are quite large here and show the expected temperature hierarchy. Now, again, where are the off-shell effects important? Well, of course, they are manifest in the scattering rate, but there's another point where they are really critical here, and that is in accessing that resonance strength, because this resonance is pretty close, or maybe even below the nominal heavy light threshold. So if you want to access, if you wish, the scattering strength, you actually have to do an off-shell integration in your transport coefficient. And that is shown here. So you can actually derive that from the Kadonov-Boehm equation that Xue Lui and Min He together we did in this paper here. And for an incoming heavy quark of momentum P, you can integrate over all the outgoing as well as the incoming light distributions, all the 3 spectral functions. And that is critical, absolutely critical to access and make use of this large interaction strength, because these spectral functions are broad, and then there's no problem to have root S values, if you wish, or total energies which probe these resonance. So another manifestation, the third one now, where the quantum effects are really important here. Otherwise, if you had bound states, you couldn't access them in two-body scattering if you just had quasi-particles. All right, so then I wanted to show one example of how we can make the connection between transport coefficients. If you have the equation of state and the spectral function, you can actually calculate the 8/S ratio, and that's what we did, and compared to the heavy flavor diffusion coefficient, both in these units which would be born at the strong coupling in the strong coupling limit. And you see that for the strongly coupled solution, they are close to the lower bound, not quite, still factor 2 above, and then with temperature they go up, while in the weakly coupled solution they are substantially larger. Now, one thing that is not obvious, what you really call strongly coupled and what is more weakly coupled. For example, is an eta over S of 4 times the upper bound, is it strongly or is it weakly coupled? It's not an obvious question. However, what we suggested, in fact, some years ago is that you can look at the ratio of these two transport coefficients. And then what you find is then in the perturbative calculation, that ratio would be 5/2, while in the strongly coupled limit, where basically they are at their quantum bound, that ratio is 1. So then you can use that ratio to look how what is its value and how does it evolve in temperature. And then you see that even for the weakly coupled scenario, where you're at 4 times the quantum bound for the eta over S, that ratio actually is quite close to the perturbative, what you expect from the perturbative calculation, while even when you are close to 2, you are not far from the lower bound. And I'm not saying yet that the T-matrix calculations do fully respect the lower bound. We haven't proven that yet, but I think this is already a suggestive plot here that tells us which tells us in terms of say a figure of merit whether we're dealing with a strongly or weakly coupled system. So the last comment before the conclusion is going back to something we I think achieved at the last heavy flavor workshop back in April. There were several things I think we achieved, but one of them that later when reviewing the plots again I found rather striking, and that has to do with the momentum dependence of the friction coefficient of the heavy quarks. So here on the left hand side we plot this 2 pi ds again, and you see that the calculations I wouldn't say all over the place, but really have a spread that is uncomfortably large. All of them are supposed to describe in fact the heavy flavor phenomenology more or less well. But then you look a little closer. In fact, you look at the momentum dependence and you see that precisely the calculations which give you a large which have a large ds in their calculation also have a very weak momentum dependence. In other words, the strength does not fall off with momentum very much. And in fact, except the green curve here, which does not fit that scheme, but all the other curves really, you go down here in different curves, you basically also go down here in the same hierarchy. So that really clearly indicates that it is critical to have a good understanding of the momentum dependence of the heavy flavor diffusion transport coefficient, friction coefficient in this case. It's really critical to control the momentum dependence if you want to narrow down this uncertainty that we currently have from the model calculations. All right, with that, I'm already done, and so I can quickly reiterate. So I discussed the thermodynamic T-matrix approach and how we can root that in various lattice data, including heavy quark free energy, quarkonium correlators, and even equation of state. And I highlighted where in this approach, and this is not exhaustive, it's just for this approach, quantum effects are critical. They are manifest to begin with in the determination of the potential. They're sort of in the self-limiting procedure that you cannot go too too strong a potential. For example, the free energy, the internal energy would not provide a solution. So it's this interplay of the large rates and the self-consistency that limits actually the potential itself. We saw that the large scattering rates or the off-shell effects are very important in the equation of state, where they even suggest the transition degrees of freedom as the partons actually melt and the hadronic resonances emerge as you go down in TC. And also in the heavy flavor transport, it is very rather important to implement these broad spectral functions to calculate the diffusion coefficient to access the large interaction strength that is provided by these quasi-bound states that emerge. So the last thing then I discussed is the connection between transport coefficients. that you would get in such an approach, and propose that maybe the ratio of this eta over S and ds can actually give us sort of a figure of merit of what really is strongly coupled. Okay, with that I'm done, and thank you very much for your attention.
Thanks a lot, Ralph. Thank you for the nice presentation. Let's see if there are questions. Okay. Just a second.
Hello, Ralph, it's Elena. Thank you for the talk. I have a question for understanding. If your spectral function has a space-like part, or it's time-like only?
No, of course, there's space-like parts. Yeah.
Okay, and then what are you doing with space-like part when you calculate transport coefficients in your formulas?
It can be integrated over. Why is there a problem?
No, it's because precisely that is related to scattering process, to real process. And
oh, that's what you mean.
Yeah, that's what for transport
coefficient.
No, yeah,
okay, so I can answer that question.
Okay.
So we have actually, that was done way back with Felix Rieck in 2010. We have, this is well known, and in particular also for the quarkonium correlators, if you go in the vector channel, you get this zero mode contribution, which is precisely that scattering part, because you turn around one of the quark lines. So what we have done is actually extract the diffusion coefficient from both the space-like limit of the vector quarkonium spectral function and from the direct calculation, and they agree pretty well. So yeah, no problem. This is fully accounted for, and it is crucial if you want to, for example, describe quarkonium J-psi correlators, because they pick up that transport peak at low, at zero, basically at zero energy.
Okay, I see there is a question from Francesco.
Yes, hello, Ralph. It's an experimentalist question on the point that you made in one of your last slides. So namely the dependence of the transport coefficient, the sub-S, or the spatial diffusion coefficient on temperature and momentum with this, let's say, trends which are somehow related. So do you think that there are experimental measurements, maybe going beyond the RAA and V2, that could help in constraining the momentum dependence?
Yeah, so I was a bit pessimistic here. Or maybe raising too much dust. But yeah, I definitely think that these momentum dependencies should absolutely show up in the momentum dependence of the V2 and the RAA. And I think in your most recent paper, you have done a great job in really quantifying that in the different models. And that provides us probably for a very good basis of going back in the models and see what are really the momentum dependencies and which are maybe more favored by the data, or which are less favored, right? And of course, there are other things. It's not just this. So this is the momentum dependent of the elastic part. We haven't talked about recombination yet, and we also haven't talked about radiative parts. The radiative, is maybe a little different story, because the dependencies are already very large at rather low PT, right? But yes, I mean, if you have precision data and your newest ones are a big step in that direction, I think we can that should really provide strong constraints beyond saying, yeah, my model or somebody else's model describes the data or not, right? I think that's the way to go, the way you did it in that paper.
Okay, are there any other questions from the room or outside? No, so thanks a lot, Ralph, for this presentation.